Okay, so we found the only maximum in this problem because both of our endpoints are minimums and the only value of x when we set our derivative equal to 0 was 600 feet. So we have found the only maximum, and now we've done all these steps. We constructed the equation, we set it to 0, and we looked at our endpoint. So our last step, our final step, is a proof. And we have three different ways we can prove it. We can look at a sign diagram for a first derivative. We can do the second derivative test. And we can sketch a graph to support it. So let's look at the first derivative sign diagram, and then we'll also look at the second derivative. So if we set up our sign diagram with the first derivative, we only have the one value of 600, and we know a restricted range. So we only have from 0 to 600 would be one section we'll have to test, and the other will be from 600 to 1200. And again, remember when we test for our sign diagram, we're always testing x values in this range into our first derivative. And I always try to pick easy numbers to test. So I'm going to test at where x is at 10 in this case, because 10 is a real easy number to plug in this range. So I'm going to plug in at 10 my first derivative, and I see that it's 2400 minus our 4 times 10 would be 400, and that's definitely 40, even less than that. And that's definitely a positive number there. For this range, I think I will test in, I guess 1000 would be the easiest. And again, remember we're testing in our first derivative. So if I test in 1000 in this range, we have 2400 minus 4 times 1000, and that clearly is a negative number. So we have proven that this is a maximum, because this would be an increasing at 600, and then right at 600 it would be 0 of our derivative, and then it would go back down. This would be a negative, a decreasing. So we've proven using the first derivative and the sign diagram that my 600 is a maximum. If we wanted to use the second derivative to test it, first we'd have to find the second derivative, which is pretty easy in this case. Our first derivative is 2400 minus 4x, so our second derivative is negative 4. Since any x value, we won't have any x value to plug in, and this is a negative, when my second derivative is a negative, it's showing it's a concave down. So this also proves that it's a maximum value, because our it would have to be a concave down, our graph at this point. So we've proven it both ways that our 600 is our maximum. But wait, we have to go back up to our question. We aren't finished. They want to know the dimensions of the field. And I'm curious to know what the area is too. We don't have to write that, but they want to know our dimensions. So we go back to our original problem, and we know that our perimeter is 2400, and it's 2x plus y. Since we found our x is 600, we know our y must be 1200. So our dimensions will have to be a length, or we could say depth, of 600 feet by our width of 1200 feet. And you might be curious like I am. I want to know my max area. It turned out it was really close to our diagram there. Our area would be 600 times 1200, and that would be 720,000 feet squared. So pretty neat. One of our options came up pretty close, just with estimate. But this is the area. Our question is asking for dimensions, so I really shouldn't circle that area. I should be circling my 600 by 1200 feet. Okay. I'm just going to uncircle that and write down our area again. And then we have one more problem before we get to class. I wanted to show you one other example, a little bit different. And so you kind of have an idea of a couple examples before we try these in class. So our next example is cooking. So we got two different kinds. Our first one was about farming, and our second one is a rectangular cake dish. So a baker wants to change the cake dish by cutting out squares from the corners of a 25 centimeter by 40 centimeter rectangle tin plate. And they want to fold the metal to form the container. And they're asking what size squares must be cut in order to produce the cake dish of maximum volume. So again, we want to first understand the problem. So here we have a problem where we have another rectangle, and it has sides of 25 centimeters by 40 centimeters. Our material is tin, and I'm going to have to cut out the same size square of each corner. And I want again find a maximum, and this time a volume, a maximum volume. So a little bit different than area. They want some maximum volume. So let's think about that, and let's write down a picture. So let's just start with a straight rectangle here. And we have 25 by 40, so let's say the 25 is here, and then our 40. So this would be our 40 centimeters, and this would be our 25 centimeters. And they're asking us to cut out a corner on each side here. So, and it's a square they want us to cut. We don't know what length, that's what we have to figure out. But each corner is going to have the same type size square being cut out of each corner. Right, so interesting. Let's call the length of the sides of this square, let's call that x. That's our one of our unknowns. So each of this, the square is going to be the length of x by x. So in our picture, we're actually not going to have a total of 25 here. It's going to be 25 minus an x and another x. So 25 minus 2x. For this side. And the same thing here, this side here will be 40 minus, we'll have another x and another x, so it'll be 40 minus 2x here. Okay, now I think my picture is okay. I know my units is centimeters, so I'll have to bring that back later. Let's think of now we want to produce the maximum volume. So our volume formula for a this type of shape would just be our length times our width, right, times our depth. And our depth in this case, since this is going to be a square, that's going to be our is going to be x. So we know it will be 40 minus 2x times 25 minus 2x times x. And we are already in the same variable, so that was nice. A little bit easier for this problem. We already have it set up from our picture to be all with the same variable. And this will end up being centimeters cubed. Alright, so this is pretty simple. We'll just have to do a little algebra here. Let me first multiply x through on this side. Okay, we have after we've multiplied through this x, we could do two things here. We could FOIL this out and have one equation here that we will take our derivative of, or we can see that our volume is in with two expressions, and we can use the product rule. I think I want to go ahead and stop and use the product rule rather than multiply through, because our two items here, my u and v, are pretty simple. So I think it actually will be simpler to not multiply through, and I will just take my derivative at this point. Because our next step, remember, will be taking our derivative and set equal to 0. So here's my v, and let's go ahead and use the product rule. My u is 40 minus 2x, and my u prime would be negative 2. My v is 25x minus 2x squared, and my v prime would be 25 minus 4x. So let's go ahead and take the derivative. We have minus 2, our u prime, times my v, plus my v prime times my u. Okay. Let's go ahead and pause the video and allow you to finish this multiplication out and set equal to 0, and then I'll bring you back. Okay, so I left you here to go ahead and multiply that through, and you should have gotten negative 50x plus 4x squared plus, and then when you FOIL this, you'd have 1,000 minus 50x minus 160x plus 8x squared. Then we're going to combine like terms and set equal to 0, because we want to find our maximum x. So we combine like terms. We have 4x squared and 8x squared for 12x squared, and our x's would equal to negative 260x, and then we have plus 1,000. Then we'll look to factor so that we can find our two x values where they're set equal to 0. So see that there's a common factor of 4, so I factor that out, and we're left with 3x squared minus 65x plus 250. Then I factored this trinomial and got 3x minus 50 times x minus 5. So then, using the zero product property, I can find my two x values. So we have 3x equals 50 if I set 3x minus 50 equal to 0, and x could be 50 divided by 3, or my other one, x set in x minus 5 equal to 0 means x equals 5. Alright, 5 sounds okay, but this 50 over 3, that seems way too big if we look at our graph. That's going to go, this side won't have anything left to it, because 50 over 3 would be, I think, 16 and 2/3. So that's too big. So that's impossible. So we can cancel that x out. So our only option here is when x equals 5. So that's one of our restrictions. This one won't work. Okay, so let's try your sign diagram to prove that this is a maximum. Also, look at your second derivative, and then I'll bring you back. Okay, so I plugged in at 5 for my first derivative and proved that it was a maximum. Here's my plug-in values. And then for my second derivative, I showed